Why classical AI languages like Lisp and Prolog are out of favor. When I was a graduate student, the intersection between cognitive psychology and artificial intelligence was one of my research areas. At that time, I learned Lisp, a dialect of Lisp and one of the classic AI languages. The programs that I wrote for the experiments conducted for my dissertation were in Lisp. As you can see, Lisp programming is characterized by many brackets. There are many jokes about it, such as lots of irritating silly parentheses, lots of insipid and stupid parentheses, and lost in a sea of parentheses. However, Lisp gradually fell out of popularity after my graduation. Since the resurgence of AI in 2022 following the breakthrough of ChatGPT, one might have expected classical AI languages such as Lisp and Prolog to experience a revival. Yet that revival did not occur. Although Prolog continues to appear in certain niche rule-based systems and logical engines where traceability and formal reasoning remain important, classical AI languages have largely become marginalized. Several factors explain this historical and technological shift. First, the shift from logic to statistical pattern. The first factor concerns the paradigm shift of AI itself. Since the early days of artificial intelligence, two intellectual traditions, symbolism and connectionism, have shaped the field in very different ways. Symbolism, often referred to as GOFAI, good old-fashioned AI, assumes that intelligence arises from the manipulation of explicit symbols according to formal logical rules. Lisp was explicitly designed for symbolic manipulation, and Prolog was built around formal logical inference. The goal was to program intelligence by specifying rules, predicates, and inference structures. Although other rule-based and knowledge representation languages also emerged during the symbolic era, Lisp and Prolog became the most enduring and emblematic representatives of classical AI. By contrast, connectionism models intelligence as emerging from networks of simple processing units inspired by neurons. Rather than encoding rules, neural networks learn statistical patterns from data through optimization procedures. The modern deep learning revival, associated strongly with researchers such as Geoffrey Hinton, demonstrated that scaling data and computation often produces superior results compared to handcrafted symbolic rules. Simply put, Lisp Prolog logic follows a structure such as, if X and Y, then Z, whereas modern AI systems operate more like, given massive statistical exposure to language or images, Z is the most probable continuation. The pattern-seeking approach proved far more adaptable to ambiguity, noise, and real-world complexity, areas where purely rule-based systems struggled to scale. Second, the hardware lottery and ecosystem. The second factor is infrastructural rather than philosophical. The resurgence of AI was fueled by GPUs, graphics processing units, which are extraordinarily efficient at performing the large-scale matrix multiplications required for deep learning, such as computing operations of the form y equals wx plus b. Neural networks align naturally with parallel computation architectures, allowing them to exploit thousands of GPU cores simultaneously. This phenomenon is sometimes described as the hardware lottery. The paradigm that benefits most from prevailing hardware capabilities tends to dominate. Symbolic systems did not receive comparable acceleration benefits from GPUs. However, hardware alone does not explain the marginalization of Lisp and Prolog. Third, the rise of Python. Python became the dominant glue language for AI not necessarily because it is more elegant, Lisp is arguably more conceptually powerful, but because it integrated seamlessly with C++ and CUDA-based libraries and developed an unmatched scientific ecosystem. Python's rise was reinforced by several merits. 1. The development of NumPy for efficient array computing backed by optimized C code. 2. The expansion of SciPy, pandas, and scientific tooling. 3. Deep learning frameworks such as TensorFlow and PyTorch that wrap GPU kernels. 4. Interactive research environments like Jupyter Notebooks. And 5. Early and widespread adoption within academia. In contrast, Lisp and Prolog never built a comparable GPU-accelerated numerical ecosystem. In modern AI, ecosystems generate powerful network effects. Once researchers, engineers, datasets, and libraries concentrate around a stack, displacement becomes extremely difficult. 4. The black box versus white box problem. Another factor concerns interpretability. Lisp and Prolog systems are transparent or white box by design. One can trace each logical inference step explicitly. In symbolic systems, if the machine concludes Z, the reasoning chain, if X and Y, therefore Z, can be inspected directly. This property is highly valuable in legal reasoning, compliance systems, and safety-critical domains where auditability is essential. Modern neural networks, especially large language models, are often described as black boxes because their reasoning is distributed across millions or billions of parameters rather than expressed as explicit symbolic chains. However, this characterization should be nuanced. There is now an active research field devoted to interpretability and mechanistic analysis, including attention visualization, feature attribution, sparse autoencoders, and circuit-level investigations. Furthermore, there is a growing movement toward neuro-symbolic AI that attempts to integrate logical reasoning with neural statistical learning. Nonetheless, in practical industry deployment, performance frequently outweighs interpretability. If a model achieves superior predictive accuracy, scalability, and adaptability, it is often preferred even if its internal reasoning is less transparent. The market has rewarded statistical and predictive power over symbolic clarity. Convergence via DSL and functional absorption. Interestingly, Lisp has not disappeared. Rather, its ideas have diffused into mainstream programming languages. Many concepts pioneered in Lisp are now standard across modern languages, including 1. Garbage collection. This automated memory management system frees developers from manually deallocating memory, preventing common errors like memory leaks. 2. First-class functions. In this model, functions are treated like any other variable, meaning they can be passed as arguments, returned from other functions, and assigned to constants. This flexibility is the foundation for creating modular and reusable code blocks in modern languages like JavaScript and Python. 3. Closures. A closure allows a function to remember and access the environment in which it was created, even after that outer scope has closed. 4. Higher-order functions. These are functions that take other functions as input or produce them as output. 5. Functional programming paradigms. This approach emphasizes the use of pure functions and immutable data to avoid side effects and shared state. Modern software architecture increasingly adopts these principles to make code more predictable, testable, and easier to parallelize across multiple processors. N6. REPL-driven development environments. The read-eval-print loop allows developers to interactively run code and see results in real time without the need for a full recompile. This immediate feedback loop, pioneered by Lisp, remains the gold standard for rapid prototyping and exploratory data analysis today. Take all of the above into account, modern Python, JavaScript, Scala, and even C++ incorporate functional constructs once considered uniquely Lispy. In large-scale computing systems, map-reduce paradigms reflect functional principles. In machine learning frameworks, computational graphs resemble symbolic expressions. Thus, instead of reviving Lisp explicitly, the software industry absorbed its most powerful abstractions. One could argue that contemporary programming is Lisp-influenced, even if the parentheses are gone. Is there still hope for classical AI languages? There remains a small but passionate community around Clojure, a modern Lisp dialect that runs on the Java virtual machine. Clojure has attracted advocates in data engineering because of several architectural strengths, including 1. Immutability by default. By treating data as unchangeable, Clojure eliminates the risk of accidental state changes. 2. Concurrency-friendly architecture. The language utilizes sophisticated software transactional memory and persistent data structures to manage multiple tasks simultaneously without the traditional headaches of manual locking. 3. JVM interoperability. Running on the Java virtual machine allows Clojure to seamlessly tap into the vast ecosystem of industrial-strength Java libraries and tools. And 4. Macro systems enabled by homogeneity. Homogeneity, the property that code and data share the same structural representation, allows powerful macro systems in which developers can effectively extend or reshape the language to suit domain-specific problems. Open source legend Nathan Mars, a prominent programmer and entrepreneur based in Hawaii, remains one of Clojure's most vocal champions. Best known as the creator of Apache Storm, which pioneered reliable, large-scale real-time data processing, Mars continues to influence the architecture of modern data systems. In a talk titled A Data-Driven Approach to Balancing Quality, Latency, and Cost in AI Agents, Mars made a compelling case for the lineage. He argued that Clojure is significantly underappreciated by the broader tech community, suggesting that its actual utility and power warrant a user base 40 times larger than its current size. For many developers, those brackets in Lisp or Clojure look like visual noise. However, for many Lisp programmers, parentheses are not clutter but a gateway to meta-programming flexibility. Clojure addressed one major weakness of earlier Lisps by leveraging the JVM ecosystem rather than rebuilding everything from scratch. Nevertheless, reviving classical AI languages at scale would require reconstructing an entire data science infrastructure comparable to Python's ecosystem, including tensor libraries, GPU integrations, model hubs, dataset tooling, and massive open-source collaboration. That represents a formidable coordination challenge. In the end, the decline of classical AI languages is not a story of intellectual failure but of paradigm shift, hardware alignment, and ecosystem dominance. Symbolic AI did not disappear because it was conceptually wrong. Rather, statistical learning aligned better with available hardware and the explosion of big data. Whether future technological shifts might once again rebalance the landscape remains an open question. So, where shall we go next? Should we continue consolidating around dominant AI ecosystems such as Python, C++, CUDA, and SQL, languages that currently define the infrastructure of modern machine learning? Or is there value in reinvesting intellectual and engineering energy into Clojure and other classical AI traditions that emphasize symbolic power and language extensibility? Is the future determined by ecosystem gravity, or is there still room for paradigmatic diversity? I welcome your perspective. If these reflections resonated with you or sparked new questions, feel free to share your thoughts and join the discussion. If you found this presentation informative, please like, share, and subscribe. Thank you for watching. Goodbye.